Welcome to Physics for Real, and today we're going to look at capacitors, and we're going to have a look at a question to start off with. So here we go. Right, so what we've got here is a capacitor, and we're given various bits of information about this capacitor. So we're going to try and answer this question. Okay, so the first thing to notice is that we're told the dimensions of the capacitor, so its length and width of each plate, or the height and width, whatever you want to call it. And that allows us to work out the area of the plate. And we're also given some other information. We're given the capacitance of the capacitor. And what we're asked to do is calculate the separation of the plate D. All right. So to do this, we need to start with an equation. And the equation we need is C equals epsilon naught A over D. Now in this equation, A is the area of a capacitor plate, one area of each of the plates. D is the distance between them. Epsilon naught is the permittivity of free space. So that is epsilon naught. We do that. Epsilon naught equals 8.85 times 10 to the minus 12 farads per meter. Okay, so that's a constant. Right, so first of all, we're going to work out A, the area. So the area is equal to 18 times 10 to the minus 2 multiplied by 18 times 10 to the minus 2, because it's the width times the height, or the width times the length. That gives us the area of this plate, which happens to be square, or a cuboid if you take into account its thickness as well, but we don't need to worry about that. So what you'll notice here is I've changed it into meters by using the times 10 to the minus 2 factor, and that means then that it'll be easier for us later on when we use this data. So that's going to give us 324 times 10 to the minus 4, and that's meters squared, and we can write that then as 3.24 times 10 to the minus 2 meters squared. So that's our area. We've got epsilon naught, and we also have capacitance because that's there. So all we need to do now is rearrange the equation. So D is equal to epsilon naught A, over C. Okay, so that's going to give us, probably better write this down here. There. D equals 8.85 times 10 to the minus 12 multiplied by the area, which is 3.24 times 10 to the minus 2, and then going to divide all that by 2.0 times 10 to the minus 9, because it's nanofarads. Okay, and that's going to give us a final answer then of D equals 1.43 times 10 to the minus 4 meters. Okay, and that's the distance between the plates D. All right, so that's that bit done. And on to the next bit. Right, so if we clear the screen here, let's clear that page, and we move down. We're now asked to calculate the capacitance of this combination here. And the way we're going to do that is basically we're going to treat the parallel section first. So these two capacitors are in parallel, okay, and this parallel section then is in series with this capacitor here. So capacitors in parallel, to work out their capacitance, you just simply work out the total capacitance by C1 plus C2. So in this case, it's going to be 2 plus 2 gives us 4.0 nanofarads, okay, for the first bit. So that's this section here, okay. So basically now we can redraw this if we wanted to. We could redraw it as one capacitor there like that, another capacitor there like that, and we can join them together. Apologies for the slightly messy drawing. So that is 4.0 nanofarads, and that is 6.0 nanofarads. So essentially that's what we've got now. We've combined this parallel capacitor into one capacitor that is needed to replace that. We could call that the equivalent capacitor. So now that we've got these two in series, so we've got this one and this one in series, we can now work out the combined capacitance of those two. And to do that, we need to use the equation 1 over Ct is equal to 1 over C1 plus 1 over C2. Okay, so capacitors in series, we use that equation that I've just written to work out their capacitance. It's kind of the opposite of resistors. Resistors in series, you just add them up, and then resistors in parallel, you combine their reciprocals. It's the opposite way around for capacitors. Capacitors in series, you combine their reciprocals. So that's going to be 1 over 4 plus 1 over 6. Okay, so if we multiply the top of this one by 3 and that by 3, and we multiply the top of this one by 2 and that by 2, we're going to get 3 over 12 plus 2 over 12, which is going to equal 5 over 12. Okay, so if 1 over Ct is 5 over 12, then Ct over 1 is equal to 12 over 5. Ct over 1 is just Ct, and 12 over 5 as a decimal is 2.4 nanofarads. So that's our solution there. Okay, so on to the next bit. Oops. So with this bit here, we're now looking at show that the charge stored on a 2 nanofarad capacitor is 18 nanocoulombs. So basically what we've got here is we've got the same capacitor setup as we had before. Okay, but we're asked now to work out the charge on the 2 nanofarad capacitor. So we're working out the charge on this one here or on this one here. Okay, it doesn't matter, it's going to be the same on both. Okay, so to do this, we're going to first of all work out the charge flowing in the circuit. Okay, so to do that, we're going to calculate the total charge flowing in this circuit. Okay, you can call it CT, and the way to do that is to have the combined capacitance and multiply that by the voltage. Okay, so the combined capacitance of these, we worked it out earlier, didn't we? It was 2.4 times 10 to the minus 9. Okay, oops, just tidy that up. So I'm 10 to the minus 9, and we're going to multiply that by 15. Okay, so that's going to give us 3.6 times 10 to the minus 8 nano, 3.6 times 10 to the minus 8 coulombs. And we could also write that as 36 times 10 to the minus 9 coulombs. Okay. So that's, sorry, capital C. Right, so we then want to work out the voltage across this capacitor. So we want to work out the voltage across here. So essentially now we know that this is our negative terminal, this is our positive one. We know that there's we know that a charge is going to flow this way. So negative electrons are going to flow along here, down here, onto this plate. Okay, and we know that that charge that flows onto there is going to be Ct, which is equal to 36 times 10 to the minus 9 coulombs. So that's going to flow onto this plate and make this negative, and then this plate here. So if 36 times 10 to the minus 9 coulombs flows onto this plate, okay, and that's a negative value, by the way, okay, then that's going to mean that the same charge has to flow off this plate. The same charge needs to flow off there, okay, and that charge then is going to flow along here. Some of it will flow that way, and some of it will flow that way. So we could say, if this is, if we'll call this capacitor C1, this capacitor C2, and this capacitor C3, we know that the charge QT, this charge here, is going to be split between this capacitor and this capacitor. It's going to split along here like this, okay? Now, because the two capacitors are the same size, it would stand to reason that this charge here is going to split in two to go along these 2 points, okay? Now we can prove this though, although it stands to reason and it's kind of logical, we can also prove it. So the way that we're going to do that is we're going to work out this voltage here. We'll call this voltage V1, okay? So V1 is going to be equal to the charge that flows onto that capacitor, which is 36 times 10 to the minus 9, divided by the capacitance, okay? So 6 times 10 to the minus 9 there. That's supposed to be a 0, but I'll just get rid of that. Okay, and the equation I should have said there is V equals Q over C. All right, so that gives us then 6 volts. Okay, so 6 volts. So we now know that there's 6 volts across here. Okay, so what that tells us then is that if there's 6 volts across here, maybe I'll change the color here. If this is 6 volts across there, okay, so that is 6 volts, then we know that the voltage across here has to be 9 volts. How do we know that? Well, because this voltage here, 15 volts, has to be 6 plus 9, okay? Basically what we've got is we've got this and this in series, and when components are in series, the voltage is shared across them. You should know that from your AS studies, okay, or your lower sixth studies, whatever you want to call it. So now that we know that this is 9 volts across, we know that this is 9 volts across the capacitors in parallel, we can then work out the charge on each capacitor, because Q is equal to the capacitance of the capacitor multiplied by the voltage. Okay, so the capacitance of the capacitor is 2.0 times 10 to the minus 9 multiplied by 9. Okay, so that's going to give us 18 times 10 to the minus 9 coulombs. So that is the charge on this capacitor here, and it's also the charge on this capacitor here. Okay, it's the same on both. Now, if we just rub a little bit of this out, essentially what we're saying here is, if we call this one, we called this one, I think, C2, didn't we? And this one's C3. Then what we're saying is that on this plate here, you're going to have a negative charge of Q2, and on this plate here, you can have a positive charge of Q2. On this plate here, you can have a charge of Q3 and minus Q3 on this plate, okay? And this charge here is Q2, but it's also Q3, okay? It's the same charge on that capacitor and that capacitor, because the charge that's flowed off this capacitor has basically split in two. Right, so on to the last bit of this question. It then says calculate the total energy stored in the capacitor combination. So to do that, we're just simply going to use the equation E equals half CV squared. Okay, so we know the combined capacitance. Let me do that again, sorry. So we know that the combined capacitance of the whole combination is 2.4, whoops, I'm in trouble here, 2.4 times 10 to the minus 9. And we know that the voltage across the combination of capacitors is 15, so we just square that, and that's going to give us an answer of 2.7 times 10 to the minus 7 joules, okay? So that is that question complete.